Welcome to this quiet journey through the cosmos, a gentle exploration designed for those peaceful moments when the day has ended and the night stretches out before you like an endless ocean of possibility. Wherever you are right now, whether you are lying in bed with the covers pulled up softly around you, or sitting in a comfortable chair with the lights dimmed low, or perhaps resting on a couch in that perfect position where your body feels weightless and supported all at once, I invite you to settle in completely. Let your shoulders drop away from your ears. Let your jaw unclench if it has been holding tension. Let your breathing slow down to match the rhythm of calm waves touching a distant shore. Feel the surface beneath you supporting your weight entirely so that you do not have to hold yourself up anymore, so that you can simply exist without effort in this moment. Tonight we're going to drift together through the vast quietness of space, not rushing or chasing after facts and figures, but floating peacefully through one of the most profound mysteries that exists in all of cosmology, a puzzle that touches on the very nature of reality itself. We will explore the question of where half the universe has gone, why when we count all the matter we can see and detect, we find that we can only account for about half of what should be there, and where the missing half might be hiding in the darkness between the stars. But we will take our time getting there, moving slowly like light traveling across billions of years, letting each concept settle into your mind gently before moving on to the next. There is no hurry in the cosmos. The universe has been here for nearly 14 billion years, and it will continue for trillions more. And in that vast expanse of time, this moment right now is yours to simply be at peace, to let your thoughts become as soft and diffuse as a nebula, to allow yourself to sink deeper into comfort with every breath you take. So close your eyes if you have not already, or let them rest half open and unfocused on some dim point in the room, and together we will begin our slow journey outward from Earth, leaving behind the bright lights and loud sounds of daily life, ascending gently through the atmosphere, rising past the edge of space where the sky turns black and stars appear in countless numbers, and then continuing outward into the cosmic ocean where matter, both visible and invisible, shapes the structure of everything we see. We begin now, drifting peacefully toward an understanding of the missing half of the universe, the census of the cosmos. As we begin our slow ascent into the cosmos, let us first consider what we mean when we speak of the matter in the universe, for matter is the substance from which everything visible is made. The atoms that compose planets and stars and galaxies in our own bodies, and understanding how much matter exists and where it is located is one of the fundamental questions of cosmology. Matter, in the most basic sense, is anything that has mass and takes up space, and in our everyday experience, matter comes in forms we can see and touch. Solid objects like rocks and liquids like water and gases like air, all composed of atoms, which are themselves composed of smaller particles called protons and neutrons in the nucleus and electrons orbiting around. These atoms combine in countless ways to form molecules and materials, and collections of atoms and molecules form all the structures we see around us, from grains of sand to mountains to planets to stars. When astronomers look out into space with telescopes, they see matter in many forms: glowing clouds of gas illuminated by nearby stars, dense clouds of dust that block light from more distant objects, planets reflecting the light of their parent stars, and most prominently stars themselves. Enormous spheres of gas where nuclear fusion in the core produces the energy that makes them shine. Stars are gathered together by gravity into galaxies, vast collections of hundreds of billions of stars bound together into rotating disks or elliptical clouds. And galaxies themselves are grouped into clusters containing hundreds or thousands of galaxies. And these clusters are connected by filaments of galaxies stretching across hundreds of millions of light years, forming what astronomers call the cosmic web, a vast structure that fills the observable universe. When we add up all the matter we can see directly, all the stars in all the galaxies, all the glowing gas between the stars, all the planets and dust and everything else that emits or reflects light, we find that this visible matter makes up only a small fraction of the total mass that must be present in the universe based on other observations. The first hints that something was missing came in the 1930s when an astronomer named Fritz Zwicky was studying the motions of galaxies in a large cluster called the Coma Cluster, measuring how fast the individual galaxies were moving relative to each other by observing the Doppler shifts in their spectra. What Zwicky found surprised him, for the galaxies were moving much faster than they should have been if the only mass in the cluster was the mass he could see in the form of stars and gas. According to Newton's laws of gravity, objects in orbit around a center of mass move faster when there is more mass pulling them inward, and by measuring the velocities of the galaxies, Zwicky could calculate how much total mass the cluster must contain to keep the galaxies bound together rather than flying apart into space. The result was startling, for the total mass needed to explain the galaxy velocities was about 400 times larger than the mass of all the visible stars and gas, suggesting that most of the cluster's mass was invisible, present only through its gravitational effects. Zwicky called this invisible mass dark matter, and he proposed that it must be some form of matter that does not emit or absorb light, making it invisible to telescopes but still exerting gravitational force on the visible matter. At the time, Zwicky's observations were largely ignored or dismissed as possibly erroneous, for the idea of vast amounts of invisible matter seemed strange and unnecessary. But over the following decades, more and more evidence accumulated that dark matter is real and that it exists not just in galaxy clusters but throughout the universe, in individual galaxies and in the vast spaces between galaxies, making up the majority of all matter that exists. The evidence came from many different observations, from the rotation curves of spiral galaxies that show stars orbiting faster than expected at large distances from the galactic center, to the bending of light from distant objects by the gravitational fields of galaxy clusters in a phenomenon called gravitational lensing, to the patterns of temperature variations in the cosmic microwave background radiation that reveal the distribution of matter in the Shirley universe. And all of these observations point to the same conclusion, that visible matter is only a small part of the total matter content of the universe, perhaps only about 15%, with the remaining 85% being dark matter that we cannot see directly but whose presence we infer from its gravitational effects. What we see and what we cannot let us drift now through the different forms of matter that fill the universe, distinguishing between what we can observe directly and what we can only detect through indirect means. For this distinction is at the heart of the mystery of the missing half. The matter we can see is called baryonic matter, a term that comes from baryons, the family of particles that includes protons and neutrons, and baryonic matter is essentially what we think of as normal matter. The atoms that make up everything familiar, from the hydrogen and helium that fill stars to the carbon and oxygen and nitrogen that compose our bodies to the iron and silicon that make up planets. Baryonic matter can emit, absorb, or scatter light and other forms of electromagnetic radiation, which is why we can observe it with telescopes that detect different wavelengths, from radio waves to visible light to X-rays. Stars are the most obvious form of baryonic matter, visible across vast distances because they produce their own Hawke light through nuclear fusion. And by counting stars in galaxies and estimating typical stellar masses, astronomers can calculate how much baryonic matter is locked up in stars. But stars are not the only form of visible baryonic matter, for there is also gas between the stars, vast clouds of hydrogen and helium that fill the space within galaxies and that sometimes glow when heated by radiation from nearby stars or when compressed by the shock waves from supernova explosions. This interstellar gas can be observed through the emission lines it produces, specific wavelengths of light emitted when electrons in atoms drop from higher to lower energy levels, and by measuring the strength of these emission lines, astronomers can determine how much gas is present and what its temperature and density are. There is also dust in space, tiny particles of solid material, mostly carbon and silicates, produced in the atmospheres of old stars and in supernova explosions. And while dust does not emit much light of its own, it absorbs and scatters light from stars behind it, creating dark lanes and patches visible in images of galaxies and nebulae. And by measuring how much light is blocked, astronomers can estimate the amount of dust present. Beyond the matter within galaxies, there is also matter in the vast spaces between galaxies, the intergalactic medium, which consists mostly of very hot diffuse gas that is difficult to observe because it is so spread out that it produces only faint signals. This hot gas, heated to millions of degrees by the gravitational compression as it falls into galaxy clusters, and by energy released from supermassive black holes at the centers of galaxies, emits X-rays that can be detected by space telescopes, and these observations show that there is significant amounts of baryonic matter in the intergalactic medium, in some regions as much or more than exists within galaxies themselves. When astronomers add up all these different forms of baryonic matter, all the stars and gas and dust and hot plasma, they find that it accounts for only about 4 to 5% of the total energy density of the universe, a surprisingly small fraction that immediately raises the question of what makes up the other 95 to 96%. Part of the answer is dark matter, the invisible gravitating mass that Zwicky discovered, which makes up about 27% of the universe according to measurements of the cosmic microwave background and of large-scale structure. But even adding dark matter to baryonic matter only gets us to about 32% of the total, meaning that nearly 70% of the universe consists of something else, something even more mysterious than dark matter, something that does not clump together to form structures but can instead remain smoothly distributed throughout space, something that has only recently been discovered and that we call dark energy. But our focus tonight is on matter, both baryonic and dark, and specifically on the puzzle that even when we account for dark matter, we still seem to be missing about half of the baryonic matter that should exist. Matter that was created in the Big Bang and that should still be present somewhere in the universe, but that we have not yet managed to observe directly, and finding this missing baryonic matter has been one of the major quests in observational cosmology over the past few decades. The predictions of the Big Bang. As we continue our gentle drift through the cosmos, let us consider where matter came from in the first place, for understanding the origin of matter helps us understand how much of it should exist and in what forms. And this understanding comes from the theory of the Big Bang, our best model for how the universe began and evolved. According to Big Bang theory, the universe started in an extremely hot and dense state about 13.8 billion years ago, and it has been expanding and cooling ever since, and in the earliest moments after the beginning, the universe was so hot that not even atoms could exist, but only a soup of fundamental particles like quarks and electrons and photons, all colliding with each other at enormous energies. As the universe expanded and cooled, these fundamental particles combined to form the first protons and neutrons, and then, about 3 minutes after the Big Bang, when the temperature had dropped to about 1 billion degrees, protons and neutrons began sticking together to form the nuclei of the lightest elements, primarily hydrogen, which is just a single proton, and helium, which consists of 2 protons and 2 neutrons, along with tiny amounts of lithium and beryllium. This process, called Big Bang nucleosynthesis, lasted for only about 20 minutes, after which the universe had cooled too much for nuclear fusion to continue, and so the ratios of hydrogen to helium to lithium that were established in those first minutes remain essentially unchanged today, forming a fossil record of conditions in the early universe. The theory of Big Bang nucleosynthesis makes very specific predictions about these ratios, predictions that depend on the total amount of baryonic matter present in the early universe, which in turn depends on the ratio of baryons to photons. For in the hot early universe, photons of light were far more numerous than matter particles, and the exact ratio determines how efficiently protons and neutrons could find each other and stick together to form nuclei. By observing the abundances of hydrogen, helium and lithium in the oldest stars and in gas clouds that have not been significantly enriched by later generations of stars, astronomers can measure the primordial abundances produced in Big Bang nucleosynthesis, and these measurements match the theoretical predictions remarkably well, but only if the total amount of baryonic matter is about 4 to 5% of the critical density of the universe, the density needed to make space flat according to general relativity. This prediction from Big Bang nucleosynthesis agrees beautifully with completely independent measurements from the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, for detailed observations of tiny temperature variations in the cosmic microwave background allow cosmologists to determine the amount of baryonic matter and the amount of dark matter separately, and these measurements also indicate that baryonic matter makes up about 4 to 5% of the total energy density. So we have 2 completely different methods, Big Bang nucleosynthesis and cosmic microwave background observations, both telling us the same thing, that there should be a certain amount of baryonic matter in the universe, enough to make up about 4 to 5% of the critical density, and this matter should still be present today because matter is conserved. It does not simply disappear, but only changes form, atoms combining into molecules or being ionized into separate nuclei and electrons, but with the total number of protons and neutrons remaining constant. The problem is that when astronomers count up all the baryonic matter they can observe, all the stars and gas and dust and hot plasma and galaxies and galaxy clusters, they find only about half of what the predictions say should be there, and this discrepancy has come to be known as the missing baryon problem, and solving it requires finding where the other half of the baryonic matter is hiding, what form it takes, and why it has been so difficult to detect: the warm-hot intergalactic medium. Let us float gently outward now from the bright regions where galaxies cluster together, drifting into the vast dark spaces between galaxy clusters, regions that appear empty when viewed with optical telescopes, but that may in fact contain the missing baryons we are seeking, hidden in a form that does not emit visible light but that can be detected through other means. The leading theory for where the missing baryonic matter resides is that it exists as a warm-hot intergalactic medium, often abbreviated as WAIM, a diffuse plasma of ionized hydrogen and helium spread throughout the filaments of the cosmic web, heated to temperatures between 100,000 and 10 million degrees by gravitational compression as the gas falls into the potential wells of dark matter, filaments, and by shock waves generated as gas streams along these filaments collide and compress each other. At these temperatures, the gas is too hot to emit the visible light or radio waves that we typically use to observe cooler gas, but it is not quite hot enough to emit strong X-rays like the even hotter gas found in galaxy clusters, and so it exists in a temperature range where it is particularly difficult to detect, emitting only faint signals in the ultraviolet and soft X-ray portions of the spectrum. The warm-hot intergalactic medium is predicted to exist based on computer simulations of structure formation in the universe. Simulations that start with the initial conditions measured from the cosmic microwave background, and that follow the gravitational collapse of dark matter and the flow of baryonic gas over billions of years of cosmic evolution. These simulations show that as the universe evolves, dark matter clumps together under its own gravity to form filaments and nodes, and baryonic gas flows into these dark matter structures, forming the cosmic web, and much of the gas ends up not in galaxies or galaxy clusters, but in the filaments connecting them, heated by compression and shocks to the warm-hot temperature range. And according to the simulations, this warm-hot intergalactic medium should contain a large fraction of the baryonic matter in the universe, possibly as much as 40 to 50%, which would be enough to account for most or all of the missing baryons. The challenge has been to actually observe this warm-hot gas and confirm that it exists, and that it contains the predicted amount of baryonic matter. And this has proven extraordinarily difficult because the signals are so faint, and because the gas is spread over such enormous volumes that even though the total mass is large, the density at any given point is extremely low, much lower than the best vacuums we can create in laboratories on Earth. Several observational techniques have been used to search for the warm-hot intergalactic medium, each looking for different signatures of its presence. One method uses absorption spectroscopy, observing the light from distant bright sources like quasars, which are extremely luminous active galactic nuclei powered by supermassive black holes, and looking for absorption lines in the quasar spectra that indicate the light has passed through clouds of intervening gas. When light from a quasar passes through a filament of warm-hot intergalactic medium, some of the ultraviolet photons are absorbed by highly ionized atoms like oxygen and carbon, creating absorption lines at specific wavelengths, and by measuring the strength and width of these absorption lines, astronomers can infer the temperature, density, and composition of the gas. These observations have provided tentative detections of warm-hot intergalactic medium along a few lines of sight. But the measurements are difficult and require space-based ultraviolet and X-ray telescopes because Earth's atmosphere absorbs most of the relevant wavelengths, and so only a handful of observations have been made, not enough to definitively confirm that the warm-hot intergalactic medium contains all the missing baryons. Another method looks for emission from the warm-hot gas rather than absorption, searching for the faint X-ray and ultraviolet emission lines produced when electrons recombine with ions, or when electrons collide with ions and excite them to higher energy levels. And some observations with X-ray telescopes have found hints of excess emission in the soft X-ray band that could be coming from warm, hot intergalactic medium. But again, the signals are right at the limit of what current instruments can detect. And confirming these detections and measuring the properties of the gas accurately requires more sensitive telescopes that are still being planned or developed. The cosmic web of filaments. As we drift through the space between galaxies, let us visualize the structure that cosmologists call the cosmic web. For this vast network of filaments and walls and voids is where the missing baryons are thought to reside, and understanding the cosmic web is essential to understanding where matter is located in the universe. When we map the positions of galaxies across large volumes of space, observing millions of galaxies and measuring their distances through their redshifts, we find that galaxies are not distributed randomly but are organized into a striking pattern, with galaxies concentrated along filaments that connect massive clusters, while other regions, called voids, contain very few galaxies at all. These filaments stretch for hundreds of millions of light years, and where multiple filaments intersect, we find the largest clusters of galaxies, containing hundreds or thousands of galaxies bound together by their mutual gravity. The voids between the filaments are not completely empty, but contain fewer galaxies and have lower overall matter density. And they can span 200 million light-years or more, enormous bubbles of underdense space that make up most of the volume of the universe, even though they contain relatively little mass. This cosmic web structure is a direct result of gravitational instability, the process by which small initial fluctuations in density present in the early universe as tiny variations in the cosmic microwave background, grow over time under the influence of gravity, with denser regions attracting more matter and becoming denser still, while underdense regions lose matter and become more empty. The process is driven primarily by dark matter, which dominates the mass budget and whose gravity pulls the baryonic matter along with it, creating the scaffolding on which galaxies form. Computer simulations of cosmic structure formation produce cosmic webs that look remarkably similar to what we observe in galaxy surveys, lending strong support to our understanding of how structure forms and evolves in the universe. The cosmic web exists not just for galaxies, but also for the gas that fills the space between galaxies, and this is where the warm, hot intergalactic medium is predicted to reside, filling the filaments with low-density plasma that is too diffuse to form stars, but that contains a substantial fraction of all the baryonic matter in the universe. The filaments of the cosmic web are not static, but are dynamic structures, with gas flowing along them toward the clusters at their intersections, and as gas falls into these potential wells, it is compressed and heated, creating the warm-hot phase. The temperature of the gas depends on where it is in the cosmic web structure, with gas in the dense cores of clusters reaching temperatures of tens of millions of degrees and emitting strong X-rays, gas in the filaments reaching temperatures of hundreds of thousands to millions of degrees and emitting faint ultraviolet and soft X-rays, and gas in the voids remaining cool, perhaps only 10,000 degrees or less, and emitting visible and ultraviolet light. This multi-phase nature of the intergalactic medium means that different observational techniques are needed to detect gas in different parts of the cosmic web, and no single telescope or wavelength can see all the gas, which is part of why finding the missing baryons has been so challenging. The cosmic web also evolves over time, with filaments growing and merging as the universe expands and structure continues to form, and the properties of the intergalactic medium change as well, with gas being heated by the formation of structure and cooled by the expansion of the universe, and with some gas being ejected from galaxies by supernova and active galactic nuclei, enriching the intergalactic medium with heavy elements produced by stars. Understanding this evolution and how it affects the distribution and observability of baryonic matter requires combining observations across many wavelengths with sophisticated computer simulations, and this work is ongoing, gradually building up a more complete picture of where the baryons are and in what physical states they exist. Dark matter's invisible scaffolding. Let us turn our attention now to the dark matter that forms the gravitational skeleton of the cosmic web. For understanding dark matter is essential to understanding where baryonic matter goes and why it is distributed the way it is. Even though dark matter and baryonic matter are very different kinds of substances with different properties and different behaviors, Dark matter, unlike baryonic matter, does not interact with electromagnetic radiation, which means it does not emit, absorb, or scatter light at any wavelength, making it completely invisible to all our telescopes. The only way we know dark matter exists is through its gravitational effects, the way it pulls on visible matter and on light passing through its gravitational field. We see these effects in the rotation curves of spiral galaxies, where stars and gas in the outer parts of galaxies orbit much faster than they would if only the visible matter were present, indicating that there must be additional unseen mass in an extended halo around each galaxy. We see dark matter in the motions of galaxies within clusters, where the velocities are too high for the visible matter alone to provide enough gravity to hold the cluster together. We see dark matter through gravitational lensing, where the path of light from distant galaxies is bent as it passes through the gravitational field of intervening dark matter, causing the background galaxies to appear distorted or multiply imaged. And by measuring these distortions, astronomers can map the distribution of dark matter even though they cannot see it directly. And we see the effects of dark matter in the cosmic microwave background, where the gravitational pull of dark matter in the early universe affected how baryonic matter moved, and how the temperature variations we observe today were established. All of these independent lines of evidence point to the same conclusion, that dark matter is real, and that it outweighs baryonic matter by a factor of about 5 to 6, making it the dominant form of matter in the universe. The nature of dark matter remains one of the great mysteries in physics, for despite decades of searching, we have not yet detected dark matter particles directly or identified what they are made of, and this ignorance about dark matter's fundamental nature does not prevent us from understanding its role in cosmology and structure formation. For we can study how dark matter behaves through its gravitational effects without knowing what particles compose it. Dark matter appears to be cold, meaning that the particles move slowly compared to the speed of light. And this coldness is important because it determines how structure forms, with cold dark matter clumping together efficiently on all scales from individual galaxies to the largest superclusters, while hot dark matter, consisting of fast-moving particles like neutrinos, would smooth out small-scale structure and prevent the formation of galaxies as we observe them. The cold dark matter paradigm combined with dark energy and the inflationary Big Bang model forms what cosmologists call the Standard Model of Cosmology, often abbreviated as lambda CDM, and this model has been remarkably successful in explaining a wide range of observations, from the cosmic microwave background to the large-scale distribution of galaxies to the abundances of light elements from Big Bang nucleosynthesis. Within this model, dark matter provides the gravitational potential wells into which baryonic matter falls, and the distribution of dark matter determines where galaxies form and how the cosmic web is structured. So even though we cannot see dark matter directly, we can infer its distribution by observing where baryonic matter is concentrated and how it moves. The cosmic web we see in galaxy surveys is essentially a map of the dark matter distribution, with galaxies tracing the locations of dark matter, filaments and clusters, and the missing baryons we are seeking must also be associated with these dark matter structures, residing in the halos around galaxies and in the filaments connecting them, heated and ionized and difficult to observe, but present nonetheless. The history of baryonic matter. Let us drift backward through cosmic time now, tracing the history of baryonic matter from its creation in the Big Bang to the present day, following its journey through different phases and states as the universe expands and evolves. For understanding this history helps us understand where the baryons are today and in what forms they exist. In the first 3 minutes after the Big Bang, as we discussed earlier, protons and neutrons combined to form the nuclei of the lightest elements, primarily hydrogen and helium, establishing the primordial abundances that we still observe today in the oldest stars and gas clouds. After nucleosynthesis ended, the universe continued expanding and cooling, but it remained filled with a hot plasma of nuclei and free electrons, too hot for neutral atoms to form, and in this plasma state photons scattered constantly off the free electrons, making the universe opaque to light like a thick fog where you cannot see far because light is constantly being absorbed and re-emitted. This opaque phase lasted for about 380,000 years, until the temperature dropped below at about 3,000 degrees, cool enough for electrons to combine with nuclei to form neutral hydrogen and helium atoms in a process called recombination, even though it was actually the first time that atoms were forming rather than reforming. When recombination occurred, the photons were suddenly able to travel freely without scattering off at electrons, and the universe became transparent. And these photons have been traveling through space ever since, their wavelengths stretched by the expansion of the universe from visible light into microwaves, forming the cosmic microwave background radiation that we observe today. After recombination, the universe entered what is sometimes called the Dark Ages, a period when no stars had yet formed, and the only light in the universe was the fading glow of the cosmic microwave background, growing dimmer and redder as the universe expanded. During the Dark Ages, the baryonic matter, now in the form of neutral hydrogen and helium gas, began to flow under gravity into the potential wells created by the dark matter, slowly accumulating in the densest regions where the dark matter was most concentrated, and after a few 100 million years, enough gas had collected in some of these regions that it became dense enough to collapse under its own gravity and form the first stars, ending the Dark Ages and beginning what astronomers call the epoch of ionization. The first stars were different from stars today, formed from gas that contained only hydrogen and helium with no heavier elements. And these primordial stars were likely very massive, hundreds of times the mass of the Sun, burning their nuclear fuel quickly and intensely, living for only a few million years before exploding as supernovae. And the ultraviolet light from these stars began ionizing the surrounding hydrogen gas, stripping electrons away from atoms and creating expanding bubbles of ionized gas around each star and galaxy. As more stars formed, these ionized bubbles grew and merged, and eventually, after a few 100 million more years, the entire universe was reionized, with essentially all the hydrogen in intergalactic space being ionized once again. And this is the state that persists today, with the intergalactic medium being almost entirely ionized except for a few pockets of neutral gas in the densest self-shielding regions. The reionization of the universe had important consequences for the distribution of baryonic matter. For ionized gas has different thermal properties than neutral gas. It can be heated more easily by ultraviolet radiation and by shock waves, and this heating raises the pressure of the gas, preventing it from cooling and collapsing to form stars in low-mass dark matter. Halos, effectively shutting off star formation in small galaxies and leaving much of the baryonic matter in a diffuse ionized state in the intergalactic medium rather than being incorporated into stars. This explains why when we count up all the stars and cold gas in galaxies, we find far less baryonic matter than should exist, for most of it never made it into galaxies but remained in the intergalactic medium, heated and ionized and difficult to observe. Feedback processes and baryon cycling. As we continue our gentle journey through cosmic history, let us consider the processes by which baryonic matter moves between different phases and locations, for matter does not simply fall into galaxies and stay there, but it is constantly cycling between galaxies and the intergalactic medium, driven by energetic processes collectively called feedback. Feedback refers to the ways in which stars and black holes inject energy into their surroundings, heating gas, driving winds, and sometimes ejecting material completely out of galaxies into the intergalactic medium. And these processes have profound effects on how galaxies form and evolve, and on where baryonic matter ends up. The most important feedback processes are supernova explosions, which occur when massive stars reach the end of their lives and explode with tremendous energy, releasing as much energy in a few seconds as the Sun will produce over its entire 10 billion year lifetime. And this energy heats the surrounding gas and drives shockwaves that sweep up material and accelerate it to high speeds, sometimes fast enough to escape the galaxy's gravity entirely. When many supernovae occur in a star-forming region over a short period of time, their combined energy can create what is called a superwind, a large-scale outflow of hot gas that streams out of the galaxy into the surrounding halo and beyond, carrying with it some of the heavy elements produced in the stars and enriching the intergalactic medium with metals, which is what astronomers call any element heavier than helium. Another important feedback mechanism comes from supermassive black holes at the centers of galaxies, which can accrete matter from their surroundings and release enormous amounts of energy in the form of radiation and powerful jets that shoot out perpendicular to the accretion disk, and this energy can heat the gas in the galaxy and in the surrounding cluster. preventing it from cooling and falling back into the galaxy to form new stars, effectively shutting down star formation and keeping much of the baryonic matter in a hot, diffuse state. These feedback processes mean that the baryonic matter in and around galaxies is not in a static equilibrium but is constantly being cycled, with some gas cooling and falling into galaxies where it forms stars, another gas being heated and ejected by supernovae and black holes back into the intergalactic medium, where it can remain for billions of years before eventually cooling and falling back into galaxies again. This cycling of baryons between galaxies and the intergalactic medium is crucial for understanding galaxy formation and for understanding where the missing baryons are located. For at any given time, a significant fraction of the baryonic matter may be in transit between phases, existing as warm or hot gas in galaxy halos, or in the filaments of the cosmic web, recently ejected from galaxies or slowly falling back in. And this transitional gas is particularly difficult to observe because it is not dense enough to emit strong signals, but is too diffuse to be detected easily by most telescopes. Computer simulations of galaxy formation that include these feedback processes show that feedback is essential for producing galaxies that look like the ones we observe, for without feedback, too much gas would cool and fall into galaxies, forming too many stars and creating galaxies that are much more massive and compact than observed galaxies. Feedback regulates star formation, keeping it inefficient enough that galaxies form gradually over billions of years rather than all at once, and it distributes baryonic matter throughout the cosmic web, rather than concentrating it all in galaxies. And this distribution is consistent with the idea that much of the missing baryonic matter resides in the warm-hot intergalactic medium, ejected from galaxies or prevented from ever falling into them in the first place by the heating effects of reionization and feedback. Observations and the search for missing baryons. Let us turn now to the observational efforts to find the missing baryons, for while theory and simulations predict that they should be in the warm-hot intergalactic medium, confirmation requires actual observations, and astronomers have been working for years to develop techniques and instruments capable of detecting the faint signals from this elusive material. As we mentioned earlier, one approach is absorption spectroscopy, using the light from distant quasars to probe intervening gas along the line of sight, and this method has had some success in detecting highly ionized oxygen and other metals that trace warm hot gas in the intergalactic medium. The observations are challenging because they require ultraviolet and X-ray telescopes in space, since Earth's atmosphere blocks these wavelengths, and because the absorption lines are often weak and blended with other features in the quasar spectra, making them difficult to identify with certainty. Nevertheless, several studies have reported detections of what appear to be warm-hot intergalactic medium absorbers, showing the expected properties of temperature and ionization state, and while these detections are still tentative and require confirmation, they provide encouraging evidence that the warm-hot intergalactic medium exists and contains significant amounts of baryonic matter. Another approach is to look for emission from the warm-hot gas, rather than absorption, searching for the faint X-ray and ultraviolet emission lines produced by the hot plasma, and some observations with X-ray telescopes have found excess emission in the soft X-ray band that could be coming from warm-hot intergalactic medium, particularly in the regions between galaxy clusters where filaments of the cosmic web are expected to connect clusters. These emission signals are extremely faint, requiring very long exposure times and careful subtraction of foreground and background sources, and the results remain somewhat uncertain, with different studies sometimes reaching different conclusions about whether the detected emission is real or is just instrumental noise or foreground contamination. A more recent and promising technique for detecting the warm-hot intergalactic medium uses a phenomenon called the Sunyaev-Zeldovich effect, which occurs when photons from the cosmic microwave background scatter off hot electrons in gas clouds, gaining energy in the process and shifting to slightly higher frequencies. And by mapping the cosmic microwave background in different frequency bands and looking for these small frequency shifts, astronomers can detect hot gas, even if it is too diffuse to produce strong emission lines. The Sunyaev-Zeldovich effect has been used successfully to detect hot gas in galaxy clusters, where the gas is dense enough to produce clear signals, and more recently it has been used to search for gas in the filaments connecting clusters, with some studies reporting tentative detections that suggest filaments contain hot gas at the predicted temperatures and densities for warm, hot intergalactic medium. Another approach that has gained attention in recent years uses fast radio bursts, mysterious short pulses of radio waves that originate from distant galaxies and they are thought to be produced by exotic objects like magnetars or by some other energetic processes that we do not yet fully understand. As the radio waves from a fast radio burst travel through space, they pass through ionized gas in the intergalactic medium, and this gas affects the radio waves in a measurable way, causing different frequencies to arrive at slightly different times in an effect called dispersion. And by measuring the amount of dispersion, astronomers can calculate how much ionized gas the radio waves passed through on their journey from the source to Earth. Several studies have used fast radio bursts to measure the total amount of ionized baryonic matter in the intergalactic medium along different lines of sight, and the results are consistent with the idea that the missing baryons are present in the intergalactic medium as ionized plasma, providing some of the strongest evidence yet that the missing baryon problem is close to being solved. These various observational approaches are gradually converging on a consistent picture, one in which most of the missing baryons reside in the warm, hot intergalactic medium as predicted by theory and simulations, filling the filaments of the cosmic web with low-density plasma that is difficult to detect, but that carries significant mass. The role of galaxies as baryon reservoirs. As we drift through the cosmic web, let us focus our attention on galaxies themselves. For while we have been discussing the baryonic matter in the intergalactic medium, galaxies are also important reservoirs of baryons, containing stars and gas in various forms, and understanding how much baryonic matter is in galaxies and how it is distributed helps us understand the overall baryon budget of the universe. Galaxies come in many types and sizes, from small dwarf galaxies containing only a few million stars to giant elliptical galaxies containing trillions of stars, and the amount of baryonic matter in a galaxy depends on its mass and on its history of star formation and feedback. In a typical spiral galaxy like our Milky Way, about 10% of the baryonic matter is in the form of stars, with stellar masses that can be estimated by measuring the total light emitted by the galaxy and using models of stellar populations to convert light into mass. The remaining 90% of the baryonic matter in the galaxy is in the form of gas, some of it cold molecular gas in the disk where new stars are forming, some of it warm neutral or ionized gas in the disk and in a more extended distribution, and some of it hot ionized gas in a large halo surrounding the galaxy that extends well beyond the visible disk. This hot halo gas is difficult to observe because it is very diffuse and produces only faint X-ray emission. But observations with X-ray telescopes have detected it around the Milky Way and around other nearby galaxies, and the estimated mass of this hot halo gas is comparable to or larger than the mass of all the stars and cold gas in the galactic disk, making it a significant component of the total baryonic matter budget of galaxies. In addition to the gas within the gravitational influence of a galaxy, there is also gas in the circumgalactic medium, the region surrounding galaxies out to distances of several 100,000 light-years, where gas exists in various phases, some falling into the galaxy as cold streams that feed star formation, some being ejected from the galaxy by supernovae and galactic winds, and some just residing in a diffuse halo that neither falls in nor escapes but maintains a rough equilibrium. The circumgalactic medium has been studied through absorption spectroscopy, observing the spectra of background quasars and looking for absorption lines from gas in front of the quasar, and these studies show that the circumgalactic medium is complex and multi-phase, containing gas at a wide range of temperatures and densities and that it contains a significant amount of baryonic matter, possibly as much as all the matter in the galaxy itself. The exact amount depends on the mass of the galaxy, with more massive galaxies having more extensive and massive circumgalactic media, and on the galaxy's history of star formation and feedback, with galaxies that have experienced intense star formation or active galactic nucleus activity having more disturbed and extended circumgalactic media. When we add up all the baryonic matter in galaxies, including stars, cold gas, warm gas, hot halo gas, and circumgalactic medium, we find that galaxies and their immediate surroundings contain a significant fraction of the total baryonic matter, perhaps 20 to 30%, with the remainder being in the intergalactic medium beyond the influence of individual galaxies. This division of baryonic matter between galaxies and the intergalactic medium is consistent with what simulations predict, and it reflects the inefficiency of star formation and the effects of feedback in preventing most baryonic matter from ever being incorporated into stars. The missing baryon problem, then, is not that the baryons have disappeared, but that they are not where we expected them to be, not concentrated in galaxies and galaxy clusters where they would be easy to observe, but spread throughout the cosmic web in diffuse plasmas that require specialized techniques to detect. The temperature phases of baryonic matter. Let us drift now through the different temperature phases that baryonic matter can exist in. For understanding these phases is key to understanding where different components of the missing baryons might be hiding and how they might be observed. Baryonic matter in the universe spans an enormous range of temperatures, from just a few degrees above absolute zero in the coldest molecular clouds where stars form, to billions of degrees in the hot gas near supermassive black holes and in the shock-heated gas of galaxy cluster cores. Each temperature range corresponds to a different physical state with different properties and different observational signatures, and the distribution of baryonic matter across these temperature phases has evolved over cosmic time as structure has formed and as feedback processes have injected energy into the gas. At the coldest end of the spectrum, below about 100 degrees, we have molecular gas, where hydrogen atoms have paired up to form hydrogen molecules and where other molecules like carbon monoxide and water can also exist. And this cold molecular gas is the material from which stars form, dense enough for gravity to overcome internal pressure and cause collapse into stellar nurseries. Cold molecular gas emits primarily in the radio and millimeter wavelengths through rotational transitions of molecules, and it can be observed with radio telescopes, though it requires fairly dense gas to produce detectable signals. And most of the cold molecular gas in the universe is found in the disks of galaxies rather than in the intergalactic medium. Moving up in temperature, from about 100 to 10,000 degrees, we have warm, neutral and ionized gas, often called the warm medium, which fills much of the volume of galactic disks and exists in some regions of the intergalactic medium as well. And this gas emits visible and ultraviolet light through electronic transitions in atoms, producing emission lines like the red H-alpha line from hydrogen and the green doublet from oxygen, and these emission lines are relatively easy to observe with optical telescopes, making warm ionized gas one of the most extensively studied components of the interstellar and intergalactic media. At temperatures from 10,000 to a few 100,000 degrees, we enter the realm of highly ionized gas where most electrons have been stripped from atoms, and this gas exists in the extended halos of galaxies and in some parts of the intergalactic medium, heated by supernova-driven winds and by radiation from stars and active galactic nuclei, and it emits primarily in the ultraviolet through absorption and emission lines of highly ionized species like oxygen, carbon, and nitrogen. And detecting this gas requires space-based ultraviolet telescopes since Earth's atmosphere blocks most ultraviolet light. From a few 100,000 degrees up to about 10 million degrees, we have the warm-hot phase, which is where much of the missing baryonic matter is thought to reside, filling the filaments of the cosmic web with low-density plasma that is difficult to observe because it is too hot to emit strong ultraviolet lines, but not quite hot enough to produce strong X-ray emission, existing in an observational gap between the techniques that work for cooler gas and those that work for hotter gas. This warm hot gas does produce some soft X-ray emission and some absorption lines in the ultraviolet and soft X-ray bands, but the signals are faint and require sensitive space-based telescopes to detect, and only in the past couple of decades have observations reached the sensitivity needed to start finding tentative detections of this elusive phase. Finally, at temperatures above 10 million degrees, we have hot X-ray emitting gas, which is found in the cores of galaxy clusters and around some active galactic nuclei. Heated to these extreme temperatures by gravitational compression as gas falls into deep potential wells and by energy injection from supermassive black holes, and this hot gas emits strong X-rays through thermal Bremsstrahlung radiation and through emission lines of highly ionized iron and other metals, and it is relatively easy to observe with X-ray telescopes and has been extensively studied in galaxy clusters. The distribution of baryonic matter across these temperature phases is determined by the balance between heating and cooling processes, with gas being heated by gravitational compression, by shock waves, by radiation, and by feedback from stars and black holes, and being cooled by radiation as electrons collide with ions and emit photons. And the equilibrium temperature depends on the density and the presence of heavy elements which enhance cooling. Computer simulations and theoretical predictions. Let us drift now into the realm of computer simulations, for these virtual universes have become essential tools for understanding where baryonic matter is located and in what physical states it exists, providing predictions that guide observational searches and helping to interpret the observations once they are made. Computer simulations of cosmic structure formation start with initial conditions based on measurements of the cosmic microwave background, setting up a box of space filled with dark matter particles and baryonic gas that has small density fluctuations matching the observed pattern. And then the simulation evolves these initial conditions forward through billions of years of cosmic time, following the gravitational interactions of millions or billions of particles and the hydrodynamic flow of gas as it responds to gravity and pressure, and modeling the complex physics of star formation, supernova feedback, black hole growth and feedback, radiative cooling, heating by ultraviolet radiation, and many other processes that affect how galaxies form and how baryonic matter is distributed. Modern simulations can resolve individual galaxies and can follow the detailed flow of gas within and around them, and they produce virtual universes that look remarkably similar to the real universe, with cosmic web structure, galaxies of various types and sizes, galaxy clusters, and large-scale filaments and voids. And by analyzing these simulations, cosmologists can determine where the baryonic matter ends up and in what phases it exists. The simulations consistently show that most of the baryonic matter does not end up in stars or in cold gas within galaxies, but remains in various forms of diffuse gas in the intergalactic medium and in the extended halos around galaxies, with a significant fraction, typically 40 to 50% of all baryons, residing in the warm-hot phase at temperatures between 100,000 and 10 million degrees, heated by gravitational compression and shock waves as gas flows into the cosmic web filaments. These simulations also show that the distribution of baryonic matter evolves over cosmic time, with more of it ending up in galaxies at early times when the universe was smaller and denser, and feedback was less effective at ejecting gas, and more of it being pushed into the intergalactic medium at later times as feedback becomes more important, and as the expansion of the universe lowers the overall density, making it harder for gas to cool and fall into galaxies. The simulations predict specific observational signatures for the warm-hot intergalactic medium, including the strengths and wavelengths of absorption lines that should be visible in quasar spectra, the amount of soft X-ray emission that should come from filaments, and the amount of dispersion that radio waves should experience when passing through ionized gas, and these predictions can be compared to observations to test whether the simulations are correctly modeling the physics, and whether the missing baryons really are in the warm-hot phase as predicted. So far, the limited observations that have been made are generally consistent with the simulation predictions, but the observations remain challenging and the results are not yet definitive, and more sensitive observations with future telescopes will be needed to fully confirm the predictions and to measure the properties of the warm-hot intergalactic medium in detail. The simulations also allow cosmologists to explore what would happen if the physics were different. For example, if there were no supernova feedback, or if black hole feedback was stronger or weaker, and these experiments show that feedback is essential for producing the observed distribution of baryonic matter, for without feedback, too much gas would cool and fall into galaxies, leaving very little in the intergalactic medium and creating a universe that looks very different from what we observe. The agreement between simulations that include realistic feedback physics and the observed universe lends confidence to the theoretical framework and to the prediction that the missing baryons are primarily in the warm-hot intergalactic medium, waiting to be fully detected and characterized by future observations. The cosmic microwave background and baryon acoustic oscillations. As we continue our gentle drift through cosmological observations, let us consider two phenomena that have provided crucial information about the total amount of baryonic matter in the universe, and that help us understand the missing baryon problem. the cosmic microwave background radiation and the baryon acoustic oscillations that are imprinted in the large-scale distribution of galaxies. We have mentioned the cosmic microwave background several times already, the faint afterglow of the Big Bang that fills all of space. But let us now explore in more detail how observations of the cosmic microwave background allow us to determine the baryon density of the universe. The cosmic microwave background has a nearly uniform temperature of about 2.7 degrees above absolute zero in all directions, but when we measure it very precisely, we find tiny variations. Hot and cold spots that differ in temperature by about 1 part in 100,000. And these variations contain an enormous amount of information about the early universe, encoded in the statistical properties of the pattern, in the sizes and amplitudes of the hot and cold spots, and in how they correlate with each other across different angular scales on the scale. The pattern of temperature variations in the cosmic microwave background is the result of sound waves that were traveling through the plasma of the early universe before recombination, pressure waves driven by the competing effects of gravity trying to compress the gas, and radiation pressure trying to expand it, and these sound waves created oscillations in density that show up as the hot and cold spots we observe. By analyzing the pattern of these oscillations, measuring the angular sizes at which the temperature variations are strongest and how the amplitude varies with angular scale, cosmologists can determine many fundamental properties of the universe, including the total density of matter, the density of baryonic matter specifically, the density of dark matter, the geometry of space, and the expansion history. The reason that the cosmic microwave background is sensitive to the baryon density is that baryons, unlike dark matter, interact with radiation through electromagnetic forces, and this interaction affects how the sound waves propagate through the early universe plasma. More baryons means more coupling between the radiation and the matter, which affects the amplitude and phasing of the acoustic oscillations, changing the pattern of peaks and troughs in the power spectrum of temperature variations, and by fitting theoretical models to the observed power spectrum, cosmologists can measure the baryon density with high precision. The most detailed measurements of the cosmic microwave background come from the Planck satellite, which mapped the entire sky in multiple frequency bands with unprecedented sensitivity. And the Planck results indicate that baryonic matter makes up about 4.9% of the total energy density of the universe, with an uncertainty of only a few percent, confirming and refining the estimates from Big Bang nucleosynthesis and providing a robust prediction for how much baryonic matter should exist in the universe today. The baryon acoustic oscillations that we observe in the large-scale distribution of galaxies are the descendants of the same sound waves that created the temperature variations in the cosmic microwave background. For after recombination, when the universe became transparent and the sound waves stopped propagating, the density variations they had created remained imprinted in the matter distribution. And these variations acted as seeds for structure formation, with galaxies eventually forming preferentially in the regions where the matter was slightly overdense. The result is that in the present-day distribution of galaxies, there is a slight excess probability of finding pairs of galaxies separated by a particular distance, about 500 million light-years, which corresponds to the distance that sound waves could have traveled in the early universe before recombination. And this excess is called the baryon acoustic oscillation feature, and measuring it provides a standard ruler that can be used to determine the expansion history of the universe and to test cosmological models. Future observations and new telescopes. Let us drift forward now into the near future, considering the new telescopes and observational campaigns that are planned or are already underway that promise to make significant progress in finding the missing baryons and in characterizing the warm-hot intergalactic medium. Several new space missions and ground-based facilities are specifically designed to observe into the wavelength ranges where the warm-hot gas emits and absorbs most strongly, in the ultraviolet and X-ray portions of the spectrum, and these missions will have much greater sensitivity than previous instruments, allowing them to detect fainter signals and to observe larger samples of sources. One of the most anticipated missions is Athena, the Advanced Telescope for High-Energy Astrophysics, a European Space Agency X-ray observatory that is currently in development and is planned to launch in the mid-2030s, and Athena will have a large collecting area and high spectral resolution, allowing it to detect faint soft X-ray emission from warm-hot intergalactic medium in the filaments of the cosmic web, and to measure the properties of this gas with unprecedented precision, determining its temperature, density, composition, and velocity structure. Athena will also be able to study absorption lines in the X-ray spectra of bright background sources, looking for the signatures of warm-hot gas along the line of sight, and the combination of emission and absorption studies will provide a comprehensive view of how baryonic matter is distributed in the intergalactic medium. Another important future mission is the proposed LUVOIR telescope, the Large UV Optical Infrared Surveyor, a NASA concept for a large space telescope that would observe in ultraviolet, optical, and infrared wavelengths. And while LUVOIR's primary science goals involve studying exoplanets and the formation of stars and galaxies, it would also be an excellent instrument for studying the warm-hot intergalactic medium through ultraviolet absorption spectroscopy, observing many lines of sight to distant quasars and searching for absorption lines from highly ionized species that trace warm-hot gas. On the ground, the next generation of extremely large telescopes, including the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope, will have collecting areas much larger than current telescopes, allowing them to observe fainter objects and to obtain higher quality spectra. And while these telescopes observe primarily in optical and infrared wavelengths where the warm-hot intergalactic medium does not emit strongly, they will be able to study the circumgalactic medium around galaxies and the cool and warm phases of the intergalactic medium, providing complementary information that helps build a complete picture of the baryon distribution. Another promising avenue for future observations involves fast radio bursts, those mysterious transient radio signals that we mentioned earlier. And several new radio telescopes are being built specifically to detect and study fast radio bursts in large numbers, including CHIME in Canada, ASCAP in Australia, and the Future Square Kilometre Array, which will be the largest radio telescope ever built. And these facilities will detect thousands of fast radio bursts, allowing statistical studies of the intergalactic medium along many lines of sight and providing precise measurements of the total amount of ionized baryonic matter between us and the sources of the bursts. The combination of all these future observations across multiple wavelengths and using multiple techniques should finally provide definitive answers to the missing baryon problem, confirming whether the warm-hot intergalactic medium contains the predicted amount of baryonic matter and characterizing its properties in detail. And if the observations do not match the predictions, then we will need to reconsider our understanding of how baryonic matter is distributed and what processes control its evolution, potentially revealing new physics or new astrophysical phenomena that we have not yet anticipated. The search for the missing baryons is an excellent example of how progress in astronomy often requires patient observation over many years, the development of new instruments and techniques, and the interplay between theory and observation, with each informing and guiding the other. The philosophical dimension of missing matter. As we drift through the cosmos contemplating the mystery of missing matter, let us step back for a moment and consider the deeper philosophical questions that this puzzle raises about the nature of reality and about our ability as humans to understand the universe. The fact that we can determine how much baryonic matter should exist through completely independent methods, Big Bang nucleosynthesis and cosmic microwave background observations, and that these methods agree so well, is a testament to the power of science and to the deep consistency of the physical laws that govern the cosmos. That we can then go out and try to find this matter, developing new observational techniques and building new telescopes to detect it. And that we are gradually succeeding in this quest, finding the missing baryons in the predicted locations and in the predicted physical states, demonstrates that the universe is comprehensible, that it follows rules that can be discovered and understood through careful observation and logical reasoning. But the fact that it has taken decades to find the missing baryons, that they were hiding in a form that is so difficult to observe, also reminds us of the limitations of our senses and our instruments, and of how much of the universe remains invisible to us despite all our technological sophistication. We can only observe what emits or absorbs light or other forms of radiation, and vast amounts of matter and energy in the universe do not interact with light in easily detectable ways, requiring us to infer their presence indirectly through their gravitational effects or through subtle imprints they leave on the things we can see. The missing baryons are an example of this, Matter that is there but that we could not see directly until we developed the right tools and knew where and how to look, and dark matter is an even more extreme example. Matter that we cannot see at all, and that we know exists only through gravity. And dark energy is stranger still, apparently filling all of space but interacting with nothing, except through its effect on the expansion of the universe. These invisible components, the warm-hot intergalactic medium, dark matter, and dark energy, together make up about 95% of the total energy content of the universe, leaving only 5% in the form of ordinary matter that we can see and touch and that makes up everything familiar, stars and planets and people. And this ratio is humbling, reminding us how small and peripheral we are in the grand scheme of things, how much of reality lies beyond our direct experience. Yet despite this, we have been able to figure out that these invisible components exist, to measure their properties, and to understand their roles in shaping the cosmos. And this is an achievement that should inspire wonder and pride, for it shows that consciousness and intelligence, however rare and fragile they may be, have the capacity to transcend their limitations and to glimpse truths about the universe that are not immediately apparent. The search for the missing baryons is the part of this larger human endeavor to understand nature, to map the cosmos and to comprehend the laws that govern it. And while individual scientists work on specific problems and may never solve them completely in their lifetimes, the collective effort over generations builds up knowledge, each discovery adding to what came before, each unanswered question pointing the way to new investigations. The missing baryon problem is nearly solved now, with most of the missing matter located and understood. But solving this problem has required contributions from many people using many different techniques over many years, and the solution has come not from one dramatic discovery but from a gradual accumulation of evidence, each observation adding a piece to the puzzle, each simulation refining the predictions until the picture becomes clear. This is how science typically works, not through sudden revelations but through patient systematic investigation. And the success in finding the missing baryons encourages us to think that other mysteries, even those that seem intractable now, like the nature of dark matter and dark energy, may eventually yield to the same approach. The intergalactic medium as a laboratory. Let us turn our attention now to the intergalactic medium, not just as the location of the missing baryons, but as a unique laboratory for studying physical processes that cannot be easily reproduced on Earth, or even in stars and galaxies, for the extreme conditions that exist in the intergalactic medium, the vast scales, the low densities, the range of temperatures and ionization states, make it an ideal place to test our understanding of plasma physics, radiative transfer, hydrodynamics, and other areas of physics. The intergalactic medium is the most rarefied gas in the universe, with densities in some regions as low as 1 atom per cubic meter, far lower than the best vacuums we can create in laboratories. And yet despite this extreme dilution, the total mass of gas in the intergalactic medium is enormous because it fills such vast volumes, and this gas plays crucial roles in the evolution of the universe, regulating how galaxies form and grow, transporting energy and metals from galaxies into the wider cosmos, and recording the history of ionization and of the radiation background that has illuminated the universe over billions of years. Studying the intergalactic medium allows us to probe conditions and processes that are difficult or impossible to study in other contexts, such as how gases behave at very low densities and high temperatures, how radiation propagates through diffuse media over cosmic distances, how shock waves form and dissipate in nearly collisionless plasmas, and how magnetic fields grow and influence the motion of charged particles in intergalactic space. The intergalactic medium also provides a record of the chemical enrichment history of the universe. For as stars produce heavy elements and as supernovas and galactic winds eject these elements into the intergalactic medium, the composition of the intergalactic medium evolves, changing from the primordial mix of hydrogen and helium to a gas that contains small but detectable amounts of carbon, oxygen, iron and other metals, and by measuring the metallicity of the intergalactic medium at different distances, corresponding to different times in cosmic history, astronomers can trace how chemical enrichment has proceeded over billions of years. The intergalactic medium is also affected by the radiation from all the stars and active galactic nuclei in the universe, and studying how this radiation ionizes and heats the gas provides information about the sources of radiation and about how they have evolved over time. During the epoch of rayonization, for example, the ultraviolet light from the first stars and galaxies rayonized the intergalactic hydrogen, and the pattern and timing of this rayonization appear to depend on the properties of those first sources, on how numerous they were and how much ultraviolet light they produced. And by studying the ionization state of the intergalactic medium at high redshifts, cosmologists can constrain models of early galaxy formation and of the first stars. In the present-day universe, the intergalactic medium remains highly ionized because of the ongoing ultraviolet background produced by quasars and by massive stars and galaxies. And measurements of this ultraviolet background and of its effects on the intergalactic medium provide information about the total luminosity of these sources and about how radiation propagates through intergalactic space. The intergalactic medium is also potentially a site for interesting plasma physics phenomena, such as the generation and amplification of magnetic fields, which may be weak in intergalactic space but which could still affect how charged particles move and how energy is transported. And there are speculative ideas that the intergalactic medium might contain exotic forms of matter or energy, such as primordial magnetic fields from the very early universe or akans or other dark matter. Candidates that interact very weakly with baryonic matter, and studying the intergalactic medium in detail might provide clues to these possibilities. The challenge is that the intergalactic medium is so difficult to observe, requiring space-based telescopes and very sensitive instruments, but as these observations become more feasible with future missions, the intergalactic medium will become an increasingly important frontier for astrophysics and cosmology, a vast and largely unexplored domain that promises to yield new insights into fundamental physics and into the history and structure of the universe, the connection between local and cosmic scales. As we drift through our exploration, let us consider how the study of the missing baryons connects local phenomena, the processes occurring in and around individual galaxies, with cosmic scale structures and with the overall evolution of the universe. For one of the beautiful aspects of cosmology is how phenomena at different scales are linked together, with small-scale processes affecting large-scale structure, and with cosmic evolution setting the boundary conditions for local processes. The baryonic matter we are searching for was created in the Big Bang, its total amount determined by conditions in the first few minutes of cosmic history, and this matter has been processed through generations of stars and through feedback processes in galaxies over billions of years. But the total amount remains constant, only its distribution and physical state changing as the universe evolves. The fact that much of this matter ended up in the warm, hot intergalactic medium rather than in stars or in cold gas in galaxies is as a consequence of how galaxies form and of how feedback operates, processes that occur on the scales of individual galaxies and star-forming regions, scales of thousands to millions of light years. But the cumulative effect of these local processes is to determine the large-scale distribution of baryonic matter throughout the cosmic web, affecting structures on scales of hundreds of millions of light years. Similarly, the large-scale structure of the universe, the cosmic web of filaments and voids created by the gravitational collapse of dark matter, determines where galaxies form and how gas flows, channeling baryonic matter along filaments toward galaxy clusters and creating the conditions that lead to the formation of the warm-hot intergalactic medium. So the cosmic structure sets the stage for local processes, and local processes in turn modify the cosmic distribution of baryons. This interplay between scales is one of the reasons why computer simulations are so valuable, for they can follow the evolution of structure across the full range of scales, from the entire observable universe down to individual galaxies and even to star-forming regions within galaxies, allowing researchers to see how processes at different scales affect each other, and to identify which processes are most important for determining outcomes like the baryon distribution. The simulations show, for example, that supernova feedback, a process that operates on scales of hundreds to thousands of light years as individual stars explode and drive winds, has profound effects on galactic scales, regulating star formation and ejecting gas into the circumgalactic medium, and that this ejected gas eventually spreads into the intergalactic medium, affecting the baryon distribution on megaparsec scales, and that the properties of the intergalactic medium in turn affect the next generation of galaxies by determining how much gas is available to fall into them and at what temperature. creating a feedback loop that connects scales from stellar to cosmic. Understanding this multi-scale physics is essential for understanding why the universe looks the way it does, why galaxies have the masses and star formation rates and gas contents that they do, why the intergalactic medium has the temperature and density and ionization structure that it has, and why the missing baryons ended up in the warm-hot phase, rather than in stars or in cold gas. The search for the missing baryons thus touches on almost every aspect of galaxy formation and cosmology, connecting observations of distant quasars and galaxy clusters with theories of star formation and black hole accretion, connecting measurements of the cosmic microwave background with models of how gas cools and heats in different environments, and connecting the physics of plasma and radiation with the large-scale structure of the universe. And this interconnectedness is part of what makes the problem so rich and interesting. For solving it requires bringing together insights from many different areas of astronomy and physics. And the solution, when it is complete, will deepen our understanding not just of where the baryons are, but of how the entire cosmic ecosystem functions. Dark energy and the ultimate fate of baryons. Let us drift now to consider the role of dark energy in the long-term fate of baryonic matter. For while we have been focusing on where the baryons are now and why they have been difficult to find, it is also interesting to think about what will happen to them in the far future as the universe continues to expand and as dark energy continues to drive the acceleration of this expansion. Dark energy, which makes up about 68% of the total energy density of the universe, is the dominant component, and its effects are becoming increasingly important as the universe ages. For while matter dominated the early universe and determined how structure formed, dark energy has come to dominate more recently, causing the expansion to accelerate rather than decelerate as gravity would have caused it to do in a matter-dominated universe. This acceleration has profound implications for the future, for it means that the universe will continue to expand forever at an ever-increasing rate, and structures that are not already gravitationally bound will be pulled apart by the expansion, with galaxy clusters being the largest structures that remain bound, and all larger-scale structures, the filaments and walls of the cosmic web, being stretched and dispersed. As the expansion continues and accelerates, distant galaxies will eventually recede beyond the cosmic horizon, the distance beyond which light from them can never reach us because they are moving away faster than light can travel through the expanding space between us and them, and these galaxies will effectively disappear from our observable universe, winking out one by one as they cross the horizon. In the very far future, billions of years from now, the only galaxies visible from the Milky Way or from whatever merged structure the Milky Way has become will be the galaxies in our local group, all bound together by gravity into a single supergalaxy, and all other galaxies will have been carried away by expansion beyond the horizon, leaving the local group isolated in an otherwise empty universe. The baryonic matter in these distant receding galaxies will be carried away with them, permanently removed from our observable universe, and eventually from our causal contact, meaning that no signal or influence from them can ever reach us again, and in a sense this matter will be lost to us, not gone but forever inaccessible. The baryonic matter in the intergalactic medium, the warm-hot gas in the filaments of the cosmic web that we have been searching for, will also be affected by the accelerating expansion, for as the filaments are stretched, the gas will become even more diffuse and will cool as it expands, eventually becoming so spread out that it effectively disappears, individual atoms separated by such vast distances that they might as well be in separate universes. Within gravitationally bound structures, like galaxy clusters, and eventually within the local supergalaxy that contains the Milky Way, baryonic matter will continue to evolve according to local process, with gas falling into galaxies and forming stars, and stars eventually exhausting their fuel and dying, leaving behind white dwarfs and neutron stars and black holes, and eventually after trillions of years, all the gas will be used up, star formation will cease, and the galaxies will consist only of the remnants of dead stars, slowly evaporating as individual stars are flung out into intergalactic space by gravitational interactions. Even black holes, which might seem eternal, will eventually evaporate through Hawking radiation, a quantum process that causes black holes to slowly lose mass by emitting particles, and after an unimaginably long time, 10 to the 100 years or more, even the largest supermassive black holes will have disappeared, leaving behind only a thin gas of elementary particles and photons, all at nearly the same temperature just above absolute zero, expanding forever into the void. This ultimate fate, sometimes called the heat death or the big freeze, is bleak from a human perspective, for it means that all structure and all complexity in the universe are temporary, that eventually everything will fade into a cold, dark emptiness where nothing interesting can ever happen again. But from a cosmic perspective, it is simply the logical endpoint of the processes that have been shaping the universe since the Big Bang, the expansion and cooling and the gradual dissipation of energy differences until thermal equilibrium is reached, the human quest for understanding. As we drift through these contemplations of the far future, let us return to the present and reflect on the human dimension of the search for the missing baryons. For this scientific quest is ultimately a human endeavor, driven by curiosity and wonder, carried out by people with lives and dreams and limitations, and sustained by a collective commitment to understanding the natural world. The scientists who work on the missing baryon problem are not abstract figures, but are real individuals, astronomers and cosmologists who spend years developing observational techniques, building and operating telescopes, analyzing data, running computer simulations, writing papers, attending conferences, teaching students, and gradually building up the body of knowledge that brings us closer to solving the puzzle. They work in many different countries, using facilities around the world and in space, collaborating across institutions and cultures, and their work is often painstaking and frustrating, with months or years of effort sometimes leading to null results or ambiguous detections that require follow-up observations to confirm. The process of science is rarely as dramatic or straightforward as it's sometimes portrayed in popular accounts. For every successful detection, there are many failed attempts. Every published paper represents countless hours of analysis and discussion and revision, and the path from observation to understanding is rarely direct, but is instead filled with detours and dead ends and gradual refinements. Yet despite these challenges, the scientists persist, driven by the desire to understand, by the satisfaction of solving puzzles, by the beauty of uncovering hidden truths about nature, and by the sense of contributing to something larger than themselves, to a collective human project that spans generations and that connects us to the cosmos in profound ways. The missing baryon problem is just one of many questions in cosmology and astrophysics, but it exemplifies the process by which science advances, the interplay between theory and observation, the development of new technologies and techniques, the importance of precise measurements and careful analysis, and the need for patience and persistence when tackling difficult problems. The fact that the problem is nearly solved now, with most of the missing baryons located in the warm-hot intergalactic medium as predicted by theory, is a testament to the effectiveness of the scientific method and to the ingenuity and dedication of the researchers who have worked on it. But the solution also raises new questions, for understanding where the baryons are is just the beginning. We still need to understand in detail how they got there, what physical processes determine their distribution and properties, how they interact with galaxies and with the large-scale structure, and how they will evolve in the future. And answering these questions will require further observations and simulations and theoretical work, continuing the cycle of investigation that characterizes science. The search for the missing baryons also illustrates how science is cumulative, building on previous work and incorporating insights from many different areas. For solving the missing baryon problem required bringing together observations of the cosmic microwave background, measurements of galaxy rotation curves and gravitational lensing that reveal dark matter, studies of quasar spectra and X-ray emission, simulations of structure formation, theories of Big Bang nucleosynthesis and rionization, and much else, each piece of knowledge contributing to the overall picture. And this interconnectedness is one of the great strengths of science, the way that different lines of evidence support and reinforce each other, building confidence in the conclusions and revealing inconsistencies that point to where our understanding needs to be refined. The beauty of the cosmic web. Let us drift now back to appreciate the aesthetic dimension of our subject, For the cosmic web itself, independent of the scientific questions it raises, is a structure of remarkable beauty, one of the grandest patterns in nature, and contemplating it can evoke a sense of wonder and awe that transcends the purely intellectual satisfaction of the understanding. When we visualize the cosmic web, either through computer simulations or through maps of galaxy distributions, we see a delicate lacework of filaments connecting nodes, a structure that is simultaneously orderly and complex, showing patterns at all scales from the smallest filaments to the largest superclusters, and exhibiting a kind of self-similar fractal quality where zooming in reveals similar structures at smaller scales. The filaments themselves are tens of millions of light-years long, but relatively thin, perhaps a few million light-years across, and they contain billions of galaxies arranged like beads on strings, while the voids between them are vast, nearly empty regions that give the cosmic web its foam-like character. The overall structure resembles, to human eyes, familiar patterns like neural networks in the brain or blood vessel networks in biological tissue. And this resemblance is not coincidental but reflects how certain patterns emerge naturally in systems where material is organized by competing forces. In the case of the cosmic web, gravity pulling matter together and the expansion of space pushing it apart, creating a balance that produces filamentary structure. The beauty of the cosmic web is not just visual, but is also conceptual. The elegance with which simple physical laws, primarily gravity and the expansion of space, acting over billions of years, produce such complex and organized structure from the nearly uniform initial conditions of the early universe. And this emergence of complexity from simplicity is one of the profound themes in cosmology, showing how the universe is capable of generating structure and beauty, and ultimately life and consciousness, through natural processes without requiring any external designer or purpose. The warm-hot intergalactic medium that contains the missing baryons is an integral part of this cosmic web, filling the filaments with glowing plasma that is invisible to our eyes, but that is there nonetheless, contributing to the total mass and shaping how galaxies form and evolve. And visualizing this invisible component, imagining the filaments lit up by the faint glow of soft X-rays and ultraviolet emission, adds another layer to the beauty of the cosmic web, reminding us that there is more to the universe than meets the eye, that the visible galaxies are just one component of a much larger and more complex ecosystem. When future X-ray telescopes map the warm-hot intergalactic medium across large areas of the sky, they will produce images that show the cosmic web not just through the distribution of galaxies, but through the direct emission of the gas that fills the filaments. And these images will likely be stunning, revealing structure and detail that has been hidden from us until now. And they will also be scientifically valuable, providing data that will help us understand how the cosmic web formed and how it continues to evolve. The cosmic web is not static, but is dynamic structure, with filaments growing and merging as the universe evolves, with gas flowing along them toward galaxy clusters, with galaxies moving through the web under gravity's influence, and with the entire structure being gradually diluted by the expansion of the universe. And understanding this evolution requires combining observations across many wavelengths and many epochs of cosmic time, from the cosmic microwave background that shows the initial conditions to observations of galaxies and gas at different redshifts that show how structure has grown, to detailed studies of local structure that show the final products of billions of years of evolution. And piecing together this history is one of the great achievements of modern cosmology: implications for galaxy formation. Let us turn now to consider how understanding the distribution of baryonic matter, including the missing baryons in the warm-hot intergalactic medium, has implications for our understanding of how galaxies form and evolve, for the two questions are intimately connected, and progress on one informs progress on the other. Galaxy formation is one of the central problems in astrophysics, asking how the smooth, nearly uniform distribution of matter in the early universe evolved into the diverse population of galaxies we see today, with their different masses, shapes, star formation rates, gas contents, and other properties. And while the broad outlines of this process are understood, many details remain uncertain. And the distribution of baryonic matter provides crucial constraints on models of galaxy formation. The fact that only a small fraction of baryonic matter ends up in stars with most remaining in gas in galaxies and in the intergalactic medium, tells us that star formation is inefficient, that most gas never gets cold and dense enough to collapse into stars. And understanding why star formation is inefficient requires understanding the physical processes that heat and disperse gas, preventing it from cooling and collapsing. And these processes include feedback from supernovae and from active galactic nuclei, which inject energy into the gas and drive winds that can eject gas from galaxies or prevent it from falling in, and also include heating by the ultraviolet radiation background, which keeps intergalactic gas ionized and warm, making it difficult for low-mass galaxies to accrete gas. The distribution of baryonic matter across different phases, cold molecular gas, warm neutral and ionized gas, hot X-ray emitting gas, and warm hot intergalactic medium reflects the balance between heating and cooling processes, and measuring this distribution provides tests of models that attempt to calculate these heating and cooling rates and to predict how gas behaves in different environments. The warm-hot intergalactic medium in particular is important for understanding galaxy formation because it represents a reservoir of baryonic matter that is not currently forming stars but that could potentially be accreted by galaxies in the future, and the properties of this reservoir, its temperature, density, metallicity and distribution, affect how galaxies can grow. The hot diffuse gas is difficult to accrete and must cool before it can fall into galaxies, and the cooling time depends on the gas properties. If the warm-hot intergalactic medium is metal-enriched, as simulations predict, then it has been processed through previous generations of galaxies and has been ejected by feedback. And this recycling of gas between galaxies and the intergalactic medium is an important part of the galaxy formation story. For it means that galaxies do not simply accrete pristine gas from the intergalactic medium, but instead interact with their surroundings in complex ways, ejecting gas and later reaccreting some of it. And this cycling affects the chemical evolution of galaxies and the buildup of metals in their stars and gas. Observations of the warm-hot intergalactic medium can test these ideas by measuring its metallicity and by looking for correlations between the properties of the intergalactic gas and the properties of nearby galaxies. And early results suggest that the warm-hot intergalactic medium is indeed metal-enriched, consistent with the recycling scenario. But more observations are needed to confirm this, and to measure how the enrichment varies with location and with cosmic time. Understanding where baryons are and how they cycle between different phases also has implications for the future evolution of galaxies. For if most of the baryonic matter is already in the warm-hot intergalactic medium, then there is less cold gas available for future star formation, and galaxies may eventually run out of fuel, leading to a gradual decline in the cosmic star formation rate, which has already been declining for the past several billion years, and which may continue to decline as the universe expands and as dark energy becomes increasingly dominant, spreading matter out and making it harder for galaxies to accrete new gas. The universality of physical laws. As we drift through the cosmos contemplating the missing baryons and the warm-hot intergalactic medium, let us reflect on a fundamental assumption that underlies all of cosmology and indeed all of science, the assumption that the laws of physics are universal, that they apply everywhere in the universe and at all times in the past and future, not just in the particular place and time where we happen to live and make observations. This assumption cannot be proven with absolute certainty, for we cannot visit distant galaxies or travel back in time to check whether physics works the same way there and then, but it is supported by all the evidence we have, by the fact that observations of distant objects and of the early universe can be explained using the same physical laws that we discover and test in laboratories on Earth, and by the remarkable consistency of observations across many different wavelengths, many different types of objects, all fitting together into a coherent picture when interpreted using known physics. The missing baryon problem itself provides a test of this universality, for the predictions about how much baryonic matter should exist come from applying nuclear physics and thermodynamics to the early universe. Assuming that the laws governing nuclear reactions and the behavior of gases were the same then as they are now, and the observations that confirm these predictions, the measured abundances of light elements and the properties of the cosmic microwave background show that this assumption is justified, that physics has not changed significantly over the 13.8 billion years since the Big Bang. Similarly, the prediction that missing baryons should be in the warm-hot intergalactic medium comes from applying hydrodynamics and plasma physics to the problem of how gas flows and heats in an expanding universe with structure formation, and the tentative detections of this gas that have been made are consistent with it having the properties that those physical laws predict, again supporting the idea that physics is universal. The universality of physical laws is not just a practical assumption that makes science possible, but is also a profound statement about the nature of reality, suggesting that there is a deep order to the cosmos, that the same principles govern the behavior of matter and energy everywhere and at all times, and that this order can be discovered and understood by intelligent beings like ourselves through observation and reason. This universality is part of what makes the universe comprehensible, for if physical laws were different in different places or at different times, then observations from one region or epoch would not necessarily tell us anything about other regions or epochs, and cosmology as a science would be impossible. We could not use observations of the cosmic microwave background to infer conditions in the early universe, or use observations of nearby galaxies to understand the general process of galaxy formation, or use measurements of the expansion rate today to predict the future evolution of the cosmos. The fact that we can do all these things, that observations fit together into a coherent whole, when interpreted using universal physical laws, is both practically useful and philosophically significant. For it suggests that despite the vastness and apparent complexity of the universe, there is an underlying simplicity and unity, that all phenomena are manifestations of a relatively small number of fundamental laws and principles, and that understanding these laws gives us a kind of power, not power to control the cosmos, which is far beyond our reach, but power to understand it, to see through the appearance of complexity to the underlying order, and in understanding to find meaning and beauty. The search for the missing baryons exemplifies this principle, for it involves applying laws of physics discovered and tested in laboratories and in our local cosmic neighborhood to predict and interpret phenomena in the distant intergalactic medium, and the success of this approach, the fact that we have largely found the missing baryons where theory predicted they should be, validates the assumption of universality and reinforces our confidence in the scientific method and in our ability to understand the cosmos. The ongoing journey of discovery. As we prepare to conclude our long, gentle drift through the mystery of the missing half of the universe, let us reflect on the nature of scientific progress and on how the search for the missing baryons exemplifies the ongoing journey of discovery that characterizes science. Science is not a fixed body of knowledge, but is a process, a way of asking questions and seeking answers, and this process never truly ends, for each answer raises new questions, each solved mystery reveals deeper mysteries, and the frontier of knowledge is always moving forward, opening up new territories to explore. The missing baryon problem appeared to be solved in outline decades ago when theory predicted that baryons should be in the warm-hot intergalactic medium, but confirming this solution observationally has taken decades of work and is still ongoing, and once the observations definitively confirm where the baryons are, there will still be many questions to answer, questions about the detailed properties of the warm-hot gas, about how it got there and how it will evolve, about how it interacts with galaxies and with the large-scale structure, about what role it plays in the cosmic ecosystem, and answering these questions will require more observations, more simulations, more theoretical work, continuing the cycle of investigation indefinitely. This open-ended nature of science is one of its great strengths, for it means that there is always more to learn, always new phenomena to discover, always deeper understanding to achieve, and this keeps science vital and exciting and ensures that there will always be opportunities for new generations of scientists to make contributions and to experience the satisfaction of uncovering hidden truths about nature. The journey of discovery in science is not smooth or linear, but is filled with wrong turns and dead ends and unexpected surprises. And this messy reality is often hidden in textbooks and popular accounts that present science as a series of straightforward logical steps from observation to theory to confirmation. But the actual process is much more complex and human, involving intuition and guesses, collaboration and competition, failures and frustrations as well as successes, and this complexity is part of what makes science interesting and challenging. The missing baryon problem has followed this typical pattern, with early hints and false starts, with predictions that were initially doubted, with observations that were ambiguous and required follow-up, with debates about interpretation, and about whether the evidence was strong enough to conclude that the problem was solved. And gradually, over years and decades, the evidence has accumulated, and the consensus has formed that yes, we do know where most of the missing baryons are, even though many details remain to be worked out. This gradual convergence toward a solution is how science typically works, not through sudden dramatic revelations, but through patient accumulation of evidence and gradual refinement of understanding. And appreciating this process helps us understand both the strengths and the limitations of science, its power to eventually answer difficult questions, but also the time and effort required to reach definitive answers. The search for the missing baryons also illustrates how science is a collective enterprise, with many people in many countries contributing over many years, each adding their piece to the puzzle, and with progress depending not just on individual brilliance but on the infrastructure of science, the telescopes and satellites and supercomputers that are built and maintained through public funding and international cooperation, the journals and conferences that allow researchers to communicate and critique each other's work, the educational system that trains new scientists, and the broader cultural support for science and for the value of understanding the natural world. The poetic dimension. Let us drift now into a more poetic mode, appreciating not just the scientific content, but the aesthetic and emotional dimensions of contemplating the missing half of the universe. For there is a kind of poetry in these vast invisible structures, in the idea that most of the ordinary matter in the universe is hidden from our eyes, spread so thinly through space that it is essentially invisible, and yet present in enormous quantities, filling the filaments of the cosmic web with glowing plasma that connects all the galaxies in a vast network. There is poetry in the fact that this matter was created in the first few minutes after the Big Bang, its total amount determined by conditions when the universe was only minutes old, and that it has been evolving ever since, flowing through space under the influence of gravity, falling into dark matter halos, being heated and ionized by starlight and shock waves, being ejected from galaxies by supernova, cycling between different phases and states, and all the while carrying within it the chemical elements produced by stars, the carbon and oxygen and nitrogen that are the building blocks of life, spreading these elements throughout the cosmos and enriching the intergalactic medium with the products of stellar alchemy. There is poetry in imagining this invisible web of glowing gas connecting all galaxies, a kind of cosmic circulatory system that links separate islands of stars into a larger whole, a reminder that galaxies are not isolated objects but are part of an interconnected ecosystem that extends across the entire observable universe. There is poetry in the human effort to find this hidden matter, the decades of work by scientists who built instruments and made observations and ran simulations, gradually piecing together the puzzle, driven by curiosity and by the desire to understand, working not for fame or fortune, but for the satisfaction of solving mysteries and for the joy of discovering something new about the cosmos, and succeeding largely, if not completely, in finding what they were looking for, confirming that the universe makes sense, that it follows laws that can be discovered, that reality is knowable if we are patient and clever enough. There is poetry too in the scale of the phenomena we have been discussing, in the fact that the filaments of the cosmic web stretch across hundreds of millions of light years, that the warm, hot intergalactic medium contains more mass than all the stars in all the galaxies, that the photons of the cosmic microwave background have been traveling through space for nearly 14 billion years, carrying information about the early universe, and that we, tiny creatures on a small planet, can detect and interpret these signals, can reconstruct the history of the cosmos, and can understand, at least in outline, how it all fits together. This ability to transcend our limitations, to reach beyond our immediate sensory experience, and to comprehend things that are vastly larger and older and more complex than ourselves, is one of the most remarkable capacities of the human mind, and it deserves to be celebrated not just for its practical utility, but for its own sake, as an expression of our nature as conscious beings capable of wonder and understanding. The missing baryon problem and its solution are part of this larger story of human understanding, a chapter in the ongoing epic of our species' attempt to make sense of the universe, and while this chapter is nearly complete, the epic continues, with new mysteries waiting to be explored and new discoveries waiting to be made, And this continuation is something to look forward to, a reason for optimism about the future of knowledge and about the human capacity for growth and learning. Returning to stillness. As we approach the final stages of our journey, drifting slowly back from the cosmic scales we have been contemplating toward the quiet stillness of your resting place, let us begin to release the details and to rest in the larger patterns, allowing the specific facts and observations to fade into a general sense of wonder and peace. The missing baryons are largely found residing in the warm, hot intergalactic medium as theory predicted, filling the filaments of the cosmic web with plasma that is difficult to observe, but that is there, comprising a significant fraction of all the ordinary matter in the universe, and this discovery is satisfying, closing a puzzle that has occupied cosmologists for decades. But it also opens new questions about the detailed properties of this gas, and about its role in the cosmic ecosystem, and these questions will be answered gradually as observations improve and as simulations become more sophisticated. But for now, in this moment, as you lie comfortably resting, breathing slowly and deeply, you do not need to worry about these questions, do not need to remember the details, can simply appreciate the overall story. The arc of discovery from initial predictions to patient observations, to tentative detections to emerging consensus, and the way this story exemplifies how science works, and how human beings, through collaboration and persistence, can solve difficult problems and can uncover truths about reality that are not immediately apparent. The universe is vast and ancient and filled with wonders both visible and invisible. And most of what exists is hidden from direct observation, dark matter that we cannot see except through gravity, dark energy that we know exists only through its effects on the expansion of space, and baryonic matter that is present but diffuse and difficult to detect, spread throughout intergalactic space in forms that do not emit visible light. And yet we have found ways to observe and understand these hidden components, developing new instruments and new techniques, making careful measurements, building theoretical models, running simulations, and gradually assembling a coherent picture of the cosmos that accounts for what we see and for what we cannot see, that explains the distribution of matter and energy and the evolution of structure and the ultimate fate of the universe. This picture is not complete and never will be, for there will always be more to learn, but it is impressive nonetheless. Booms. A testament to human ingenuity and curiosity. And it provides a framework for understanding our place in the cosmos, a way of seeing ourselves as part of something much larger, temporary manifestations of matter and energy that have been organized by billions of years of cosmic evolution into forms capable of contemplating their own existence and origins. As you rest here in the darkness, your body relaxed and your mind quiet, you are part of this cosmos, made of atoms that were created in the Big Bang and forged in the cores of ancient stars, atoms that have been cycling through space for billions of years, sometimes in stars, sometimes in gas clouds, sometimes in planets, and now briefly in you. And when you are gone, these atoms will continue their journey, returning to space and perhaps eventually being incorporated into new structures, new stars or planets, or even new living beings. And in this way you are connected to everything that has ever existed and everything that will exist, part of an ongoing cosmic process that began nearly 14 billion years ago, and that will continue for trillions of years into the future. The comfort of cosmic perspective. Let us rest now in the comfort that cosmic perspective can provide, the way that contemplating the vast scales of the universe can put our everyday concerns into context and can offer a kind of peace that comes from recognizing how small and temporary our troubles are against the backdrop of cosmic time and space. When we think about the missing baryons spread throughout the intergalactic medium, or about the dark matter that holds galaxies together, or about the cosmic web stretching across billions of light years, our personal worries and anxieties can seem less overwhelming, less all-consuming, for we see that we are part of something much larger than our individual lives, that the universe has been here for almost 14 billion years and will continue for trillions more, and that in this vast expanse of time and space our brief existence is just a moment, a flicker of consciousness in the eternal night, precious because it is rare, but also impermanent and small in the grand scheme. This recognition can be either distressing or liberating depending on how we approach it, distressing if we focus on our insignificance and impermanence, liberating if we focus on being part of something greater, on the privilege of being alive and conscious in a universe that is mostly dark and empty and unaware, on the opportunity we have to experience beauty and wonder and to understand, however partially, the nature of reality. The missing baryon problem and its solution are part of this understanding, a small piece of the larger picture of how the universe works, and knowing about it does not change our daily lives in any practical way, but enriches our inner lives, gives us something to think about and wonder at, connects us to the work of scientists around the world who are dedicated to uncovering these mysteries of awe, and reminds us that there is more to existence than just our immediate needs and desires, that we are capable of caring about and understanding things that have no direct relevance to our survival or comfort, but that satisfy our curiosity and our aesthetic sense. As you lie there breathing slowly, feeling your body sink deeper into the surface beneath you, feeling the weight of fatigue and the pull of sleep, you can let all these thoughts and images we have explored tonight begin to dissolve, can release any need to hold on to them or remember them in detail, for they will settle into your mind at deeper levels, becoming part of your background understanding of the world, informing how you see things and think about things, without necessarily being consciously present. And this integration happens during sleep as the brain processes and consolidates experiences. So by letting yourself sleep, you're actually helping to absorb and understand the material in a way that conscious effort cannot achieve. The cosmos will still be there tomorrow, still expanding, still filled with dark matter and dark energy and warm, hot, intergalactic medium, still evolving according to the laws of physics, and you will still be part of it, connected to it through the atoms of your body and through the consciousness that allows you to contemplate it. And this connection is permanent and unbreakable, even though your individual existence is temporary, for the matter and energy that compose you are eternal, indestructible, only changing form as they flow through the cycles of cosmic evolution. Rest now in this knowledge. Let it be a source of comfort and peace. Let the vastness of the universe be not overwhelming, but reassuring, a reminder that you are held in something larger, that your life has meaning not because of what you accomplish or achieve, but simply because you are part of this grand cosmic story, a chapter in the ongoing narrative of matter, becoming conscious and contemplating itself. And this is enough. This is beautiful. This is worth celebrating. And now, in this moment, it's time to rest, to let go, to sink into sleep as gently as a photon from a distant galaxy, drifting through intergalactic space, traveling for billions of years before finally being absorbed, before finally coming to rest. And just as that photon's journey has purpose and meaning in the larger pattern, even though it is just one photon among countless trillions, so too does your existence have purpose and meaning in the larger pattern of the cosmos. And you can rest in that knowledge, can let it support you as you drift into sleep, dissolving into the cosmic night. As we reach the final moments of our journey together, drifting through the last wisps of conscious thought before sleep takes hold completely, let us dissolve the boundaries between ourselves and the cosmos, between the observer and the observed, between the question and the answer, and rest in the simple unified awareness of being, of existing as part of the universe rather than as separate from it. The missing half of the universe is not really missing, but has been hiding in plain sight all along, spread throughout the intergalactic medium in forms that are difficult to observe, but that are essential parts of the cosmic structure. And this hiding is not intentional, but is simply a consequence of how matter behaves under the conditions that exist in intergalactic space, ionized by radiation, heated by gravitational compression, spread thinly across vast volumes. And these conditions make the matter invisible to our eyes and to most of our instruments, but do not make it any less real or any less important. In the same way, many aspects of our own consciousness and inner lives are hidden from direct observation, accessible only indirectly through behavior and through introspection, and yet they are real and important and shape who we are and how we experience the world. And this parallel between hidden matter in the cosmos and hidden aspects of self is worth contemplating, for it suggests that invisibility does not mean non-existence, that there are many layers to reality beyond what we can directly perceive, and that understanding requires looking beyond the surface, using indirect methods and theoretical frameworks to infer what we cannot see directly. The cosmos in which we find ourselves is stranger and more wonderful than common sense would suggest, filled with dark matter and dark energy and warm hot plasma and countless other phenomena that challenge our intuitions and expand our understanding. And contemplating this strangeness is part of what makes cosmology so fascinating, for it shows us that reality is not limited to what we can easily perceive or understand, that there are depths and mysteries beyond our immediate grasp. And yet these depths and mysteries are not forever inaccessible, but can be probed and understood through patient observation and creative thinking. The search for the missing baryons exemplifies this process, taking a puzzle that seemed intractable and gradually solving it through the development of new observational techniques and through theoretical insights that predicted where to look and what to look for. And the solution, when it came, was not a dramatic revelation, but a gradual accumulation of evidence, each piece fitting into the larger picture, each observation confirming and refining the theoretical predictions, until finally the consensus formed that yes, we understand where the baryons are and why they have been difficult to find. This gradual nature of discovery is typical of science and is something to appreciate rather than to regret, for it shows that understanding is achievable through systematic effort, even when quick, easy answers are not available, and it demonstrates the value of persistence and patience and of building on the work of others, for no single observation or idea solved the missing baryon problem. But rather, it was the collective effort of many scientists over many years that brought us to our current understanding. As you sink deeper into rest now, feeling your thoughts becoming slower and more diffuse, feeling the boundaries of self becoming less distinct, you can imagine yourself expanding to fill the cosmos, your consciousness spreading out like the warm, hot intergalactic medium to occupy the spaces between galaxies, connecting everything in a vast network of awareness. And in this expanded state, there is no separation between you and the universe, no distinction between the knower and the known, only the simple fact of existence, of being, of consciousness, arising from matter and energy organized in particular ways. And this consciousness is rare and precious and temporary, but while it exists, it is capable of experiencing wonder and beauty and understanding. And this capacity is worth cherishing, worth celebrating, worth protecting. And as you drift into sleep, you carry this capacity with you, dormant but not absent, resting but not extinguished. And tomorrow when you wake, it will return refreshed and renewed, ready to engage with the world again, to perceive and think and feel and wonder, and the cosmos will still be there, still vast and mysterious and beautiful, still inviting exploration and understanding, still offering infinite opportunities for discovery and growth, and you will be part of it, as you have always been, as you always will be, connected to everything through the fundamental forces and through the shared history that stretches back to the Big Bang, forward to the far future, and present in this eternal now where all of existence occurs. And now, in this moment, there is only rest, only peace, only the gentle dissolution of thought into silence, of consciousness into sleep, of self into the infinite. And this is good, this is right, this is how it should be. And you can let go completely now, can surrender to the pull of sleep, can drift away on the currents of unconsciousness, knowing that you are safe, that you are held, that you are part of something infinitely larger and more enduring than your individual existence. And in this knowledge there is peace, there is rest, there is sleep, deep and dreamless and renewing, and you're falling into it now, falling like a photon, falling into a black hole, falling like matter, falling into the cosmic web, falling like consciousness, falling into oblivion, falling gently, peacefully, inevitably into sleep, into rest, into the warm, dark embrace of night.